Chapter 2 discussed systems of linear equations, and we began to solve those systems of linear equations using matrices. So this chapter actually focuses on matrices and discusses its own usefulness, properties, and other attributes that the set of all matrices themselves actually form what's called a vector space. Now, we're not really talking about vector spaces, but we will hopefully be able to tie some of those theories into these as we study matrices a little bit more. So matrices are rectangular arrays of numbers. We usually see them, I guess before coming into this class, we saw tables that would have numbers in certain rows and columns. And so whenever you have a set of those numbers in rows and columns, you can put them together as a matrix. So let's establish some definitions. We have the size of the matrix. The size of the matrix is is given by two numbers. First, the row, the number of rows, then the number of columns. So m by n has m. M and n are the number or the letters that they use for these numbers of rows and columns. So it's a little confusing. So I'll try to make sure I enunciate the m and n properly. So an m by n matrix has m rows and n columns. And we have a couple of special matrices. Well, there's more than a couple, but two to begin with. A matrix with one row is called a row matrix, and a matrix with one column is called a column matrix. And sometimes we can take a look at vectors as either a row matrix or a column matrix, and we'll use appropriate notation when we need to.
Those A's are vectors themselves.
Yeah, so the representation where we break up a matrix into a bunch of row matrices or a bunch of column matrices, we use these things as vectors. So let's see if we can get this straight. A notation with a capital A or a B or an M will represent a matrix. Regardless of whether they're capitalized or not, if they have arrows on top of them, they'll be represented as vectors. And again, those vectors can be seen as column vectors or row vectors, whatever is more appropriate for the situation. Jamie?
I'm wondering why, if we have an m by n matrix, you would say 1 by m or n by 1.
No, maybe because I mistyped that.
Doesn't matter which way.
It doesn't matter because these are just numbers and they're arbitrary at this point. But I think Jamie has a point in being consistent. A row matrix. No, there's no point. There's no point to any of this. So yeah, maybe we should have called this a 1 by n matrix and an m by 1 matrix. Right. So yeah, just like in an xy Cartesian coordinates, you want the x to always be first.
Well, then it shouldn't be flipped now. Column matrix on the other side.
Oh boy, I don't know.
It's weird because the book defines like the first one as the up and down, and the second letter is the left to going the opposite.
To switch the M to 1 and the N to
Oh, does this actually be switched? Boy, that's even more confusing, huh? No? So 1 is the number of rows, and then n is the number of columns. So this should be n, and this should be m. So a column matrix has m rows and only one column. Okay. So the other thing about matrices, and this is where it kind of gets confusing, is they use a double subscript notation. And so A11 would be the first element in the first row and first column. A12 would be the element in the first row and second column. So the I refers to the row, and then the J refers to the column, or the first number refers to the row, and then the second number refers to the column. And we can always try to spot where a particular value is based on the row and column. And this is important particularly for computer science majors, the way they subscript things, because when you try to access a particular value from a big table of things, it's good to know how to get to that one particular value in the table. So in our case, for matrices, we go to the number of rows and number of columns.
Like if you're taking like whatever slot in in a two-dimensional array.
Yeah, so any two-dimensional arrays, for those people that have taken computer science, you're looking at how to find that one thing, one slot in a two-dimensional array, so you need a double subscript. And we're not going to go through this, but in some computer science applications it might be necessary to go to three-dimensional arrays, in which case you get 3 subscripts. So we're in matrices, we're just going to deal with 2 subscripts. Okay, the other thing about matrices is that a matrix can be broken into a set of column vectors. Is this correct now? N column. There are M vectors. So these things would have M elements. So A1 would actually be A11, A21, AM1. And that would be the column vector that would describe the first column of the matrix. And then if you just tack on a bunch of columns, squeeze this in like this, you'll be able to construct your matrix with column vectors. And similarly, you can stack them on top of each other and construct a matrix with row vectors. And they just capitalized A here just for the sake of saying it's a different vector from this little a. So, yeah.
Is the little a supposed to have the I index or the j index? Or is it not?
The little a is counting the number of columns. So if I were to put an I or a j, I'll put a j index there because it's number of columns.
Right.
And the capital A vectors are, so there should be a j. It's one of those things where it really doesn't matter, but if let's be consistent with the notation, so that should be a j. So A1, for example, is going to be the first row, so that would be A11, A12, all the way up to A1n. And we can look at this as a row vector, or a vector that's written in a row. Okay?
So is it for row vectors for capital and then for column?
Yeah, that convention about capital and lowercase is not, it's not really a convention, so it can be written many different ways. I suppose we could have put B there, but then that would have been confusing because where did B come from or something. So they decided to just capitalize A. All right, a few more interesting matrices aside from row and column matrices. We have square matrices. If your number of rows and number of columns are the same, then they're obviously a square matrix. And with square matrices, it turns out that that's a nice kind of matrix to deal with. The diagonal of a matrix are those numbers that fall in the diagonal. It says here a diagonal matrix whose entries are so a diagonal matrix would be a matrix that has zeros everywhere else except for the diagonals.
You have an X with one.
Pardon me?
Like an X pattern with those
No,
zeros.
it's just zeros. When I say zero here, I mean zero for every single value here. So these are all zeros. And usually people just put zeros on these things, assuming that this is not just one zero, but zeros in all the other slots that are not in the diagonal. So this is a diagonal matrix. A diagonal matrix whose entries are all the same is called a scalar matrix. Because if it's all the same, let's call it 3, 3, 3 in all the diagonals. Because if it's all the same, then there's a way to factor this out. And when you factor this out, you don't get just a 3, you get something else. But this is called a scalar matrix. And then the identity matrix is going to be the matrix with 1s in the diagonal. And this identity matrix is like the multiplicative identity. We'll see that later on, that when we multiply this by anything, when we get to the multiplication, that we're going to get exactly this other matrix. Yeah? Yeah, I think it needs to. So the scalar matrix is called a scalar matrix because we can actually see this as just a scalar times the identity. So if these were 3s, anybody know what that scalar is? 3? No. Seems obvious. I mean, it seems like obviously it should be 3, but it's not 3. Really? What should it be?
0.
No. 12? No. Well, it could be 12, I suppose. No, it couldn't have been 12. No, it's not 2.
1, 2, 3, 2.
It could be 3, it could be 9, it could be 27, it could be 81, 3 to the nth power, depending on how many rows you have.
So, I mean, yeah, like, it is 3.
It was 3 if it was a 1 by 1 matrix.
How do you do scalar multiplication?
Well, maybe it is 3. Hal, what do you think?
The end looks good as long as the end has the right value.
As long as it has n rows and n columns, right?
Not as long as n is 1.
So it was 3?
I feel like it should be.
It should probably be 3, huh?
Technically, you're not wrong. As long as you define it.
3 to 3 to the n. I thought it was 3 plus. Yeah, it's 3.
What do you think, Jamie?
It's 3. Why do you internet says 3?
It should be 3?
Totally 12.
12. All right, we'll call it 3. So you guys were right. Look at that. All right, well, zero matrix is
Why would it be 3 to the n? What is that for?
I think it has something to do with the elementary row operations. When you take a 3 out, multiply a row by 3, multiply another row by 3. So I think that 3 to the n was something to do with elementary row operations that I'm getting mixed up with. All right, the zero matrix is going to be a matrix full of zeros. And depending on the size, it doesn't necessarily have to be a square matrix. You can have a non-square matrix that's full of zeros. But the notation for this, just like a zero vector is a 0 with an arrow on top, I'll put a zero matrix as a 0 inside of a square brackets. And then the size of that matrix would just be whatever the size is appropriate for whatever it is we're doing. All right. Let's take a look at some matrix operations. Addition and subtraction. Oh, here's a scalar multiplication. Yeah, you do just multiply everything by that. And I don't know if we need to do examples for each one of these, but maybe we'll try to come up with some quick examples. Maybe if I just have a 2 by 2 matrix. When we add matrices, first of all, the matrices have to be the same size, otherwise you're not going to be able to add them. And if they are the same size, then each of these ij's and each of the ij's in the first matrix and the second matrix will have to match up and be added together. So we got 1 and 5 is 6. This is 7, 8. This is 10. And this is 12. If they're not the same, they don't have the same rows and same columns, then you're not going to be able to add them. So 1, 2, 3, 4 plus 5, 6, for example. you're not going to be able to add two matrices that are not of the same size. Yeah.
Doesn't matter which row is added to it.
In this case, you can't add them.
Yeah, but
In the other one, you're adding the 1-1 slot is added to the 1-1 slot here, and the 1-2 slot is added to the 1-2 slot, and you can't mix anything else up. So the addition is well defined. It's adding the specific slots.
So even if we do like some row manipulation, like say move row 2 to row 1, and then do some of the other.
I might be able to.
But also I was thinking, it might happen in the past.
3, 4, 1, 2, 3, 7, 8, plus 7, 8, 5, 6.
Well, I think the row operations is a different kind of concept than what we're doing here right now. The row operations, we'll see that there's going to be some intimate relationship between row operations and some multiplication of some special matrices. That we'll see that, and we'll see that later on. Okay, but for now, this is what we have. This is addition. They have to have the same size. The scalar multiplication just involves one matrix and a scalar, so this is the one that we were messing around with that I was getting incorrect. So 3 times identity matrix. These zeros are bigger zeros than the ones, because this is supposed to be a 3 by 3. This is going to be a 3, 3, 3, and zeros on the other slots. Or if you really want me to just put zeros all over. So a matrix multiplication is taking your scalar multiplication in the matrix is taking the scalar and multiplying it to every single one in the matrix. The difference is this is just a formal way of writing it, but you just subtract. And we don't have to do that. The additive identity is 0, the 0 matrix, and this should have been, I said my notation was going to have square brackets on the zeros, but I guess that's an O. No, it's 0. And the additive inverse is the same as the additive inverse for real numbers. You subtract them to get 0. Okay, so these are the basic matrix addition and scalar multiplication business. Anything that has to do with addition is all on this page. So our next step is to take a look at the multiplication, define a multiplication for matrices. So let's do that. And the way matrix multiplication is defined is kind of tricky. And see if we can. It's tricky because it requires you to add a bunch of products, and how you get those products is also kind of tricky. So what you have here is just like addition. Where addition has to have a certain size for your matrices, multiplication also has to follow a certain size requirement. So if you're going to multiply A times B, your A should be an M by N matrix, and your B, notice the difference between the sizes of A and B, or not the difference, but the similarities, is that the number of columns you have for A columns has to be the same as the number of rows you have for B. So that's going to be important before you actually do the multiplication, in that the columns for the first vector and the rows for the second vector have to match. And aside from that, it doesn't matter how many rows for the first vector or how many columns for the second vector. That doesn't matter. So let's see if I can just come up with a quick example of this. Let's say this is your matrix A. Your A has 1, 2, 3, 4, 5, 6. It has two rows and 3 columns. So how many columns, how many rows does my next vector have to have? It has to have the same number as the number of columns, right? So 1, 2, 3 columns. So I need 3. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to have 3 rows for this. Now, your output matrix is going to be a matrix C. And it says here the ijth element for C has to be a sum of a bunch of products. So let's pick a C vector or a C value that we're going to come up with, and let's actually assign an ij value for that. So let's see. What am I going to have in my C2 comma or 2, 3 slot? According to this is going to be, do I want to do this? I don't know if I want to do this. K goes from 1 to n. N is the, let's put the sizes here for these vectors. A is a what by what? It's a 2 by 3. B is a what by what? This is a 3 by 3. And so your n vector is a number that matches, which is a 3. So it looks like our sum is going to be adding 3 things. And it's going to add a sub I. I is equal to 2 in this case. A sub 2k and B sub k j, which j in this case is 3. So now just focusing on this, k, so this is A21, B13 plus A22. This is when k is equal to 2. B23 plus A23, B33. So what's A21? I look at my A, where's 2, 1? So second row, first column, 2, 1, so that's 4. The B13, where's B13? 3. A22, 5. Times B23, 6. And then A23, 6. And B33, 9. How many people have done matrix multiplication before? Okay. You probably don't do it like this, right? No. I wouldn't do it like this. What is this, by the way? 12, 30, 54. I lost count after 12. What is it? 96? So whatever matrix my C is going to be, my second row and third column, so 1, blank, 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 blank. My second row and third column is going to be 96. I don't know. Is this going to have 3 rows? How many? What's the size of this matrix going to be? 2 by 3? Okay, so this is how you would find each element in C. if you have done matrix multiplication before, you don't do it like this. The way to get 96 is to really do a dot product. And the dot product you would do would be the dot product between the second row and the third column, and that's going to get your second row, third column entry. Right? All this is a dot product. Right? 4 times 3, 5 times 6, 6 times 9, and then you're going to get that entry. So that's how you would do the matrix multiplication. And what is going to be our size of our final matrix coming out is going to be, this is a 2 by 3 times a 3 by 3. And these two numbers have to match up. And your final matrix outcome is going to have 2 rows and 3 columns. So your output would be a 2 by 3 matrix. So I took the first matrix is a 2 by 3 matrix. The second matrix is a 3 by 3 matrix. The middle numbers will eliminate because they should be the same. And then so the first number and the last number is going to be the size of your outcome multiplication matrix. If your original matrix had fractions, then you'll have fractions in your matrix. But if they're all whole numbers, then they shouldn't be.
Is that just an element of the...
Yeah, that's just one of the elements.
Oh, okay.
So let's continue to finish this matrix. Let's work on this matrix some more. So if I want this slot right here, it's the 1 by 1. So I'm going to take the first row in my A matrix in the first column. So that's the first row and first column. And I get 1 plus 1, or 1 times 1 plus 2 times 4 plus 3 times 7. So 21, 29, 30. 30? Right? And all we were doing is we were doing a dot product. So to find the next entry, if I wanted this entry, I would still in the first row, but this time in the second column. So the first row and the second column of the second matrix. And I would do that dot product, 2, 1, 3 dotted with 2, 5, 8. Which is whatever. 10, 12, 12 plus 24, 36. We do one over here. So this is the second row and the first column. And that would give me a 4 plus 20 plus 42, 66. Okay. So, did you guys get the idea of multiplication? Yeah.
Is there any better way to write the subscripts? Because it looks like C23. How do you know it's C?
You're hoping that your matrices that you're going to be dealing with wouldn't be larger than 10 by 10. 2, 3. If it does get larger, you just use indices like I's and J's. But this is the only way. Oh, the other way that you can do it is you can put a comma in between.
All right, okay.
Okay, is that good? Should we finish this multiplication? Okay. Because those are big numbers now. I don't like big numbers. Okay, so matrix multiplication, really some form of a dot product with combinations of x's and y's. And probably the first thing or the biggest thing you want to inspect is the size of your matrices. Make sure the size of your two matrices that you're multiplying will fit the actual product. And you should also expect the outcome of your product matrix. And so if you know those things, then just doing the dot product is going to be the other bit that you need to do. Okay, I think we have some theorems here. We have a couple of theorems of ways to extract elements. Yeah. Well, the dot product itself, you can kind of say it's commutative, but that's an important point to examine real quick. Let's talk a little bit more about matrix multiplication now that you bring that up. Multiplication. So matrix multiplication. What is it? M by N and B N by R. And then if you multiply these two things, you would get another matrix, which is an M by R. Okay? So you asked about the dot product being commutative, but I think maybe a more interesting question is matrix multiplication commutative? So can we multiply B, which is an N by R matrix, with A, which is an M by N matrix? Only if these two things are equal, yes. So you can only do the multiplication if these two things are equal. So let's say if R is not equal to M, then this does not exist. Just like the addition, they have to be the same size. For multiplication, the number of columns for the first matrix has to equal to the number of rows for the second matrix. And if they're not equal, then you can't do the multiplication. If they were equal, then you are going to get another matrix. Instead of C, let's call it D. What's the size of the matrix you're going to get? N by what? N by N. It has to be an N by N matrix, right? It's these two numbers. So just by the size, would C and D be the same? And if they happen to be the same sizes, there's still no guarantee that these two things will be equal to each other. So here we have A multiplied with B and B multiplied with A, and they are not necessarily equal to each other. So this little fact over here says that matrix multiplication is not commutative. They might equal each other, but it's not necessarily, it's not a guarantee. Yeah, it would be by accident. It would be a high coincidence if that ever happens. So this is one of those examples if you ever get into more math and you study what's called groups and fields and stuff like that, looking at things that are not commutative is pretty interesting. Everything that we've dealt with, you know, real numbers, complex numbers, and even the finite fields that we've been dealing with, they're all commutative. But there exist, they're not fields anymore, but they're groups and rings, they're called, that might not be commutative in multiplication. So this is a case where it's not. All right. So you can't just switch the order of matrix multiplication. Back to this theorem, we're doing some extracting elements. It turns out there's ways to extract elements from a matrix if you want. And we didn't really discuss standard unit vectors the way the book presented it, but a standard unit vector is a vector that's either, you know, that has 1 in one slot and zeros in the rest of the slot. So let's just say in 3D, the standard unit vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are, I'm writing them as column vectors. Also can be seen as column matrices. But these are your standard basis vectors, they're called, or standard unit vectors. And sometimes we call these the I, J, K vectors in physics. So that's what these E's are. EI or E1, E2, E3 would just be these vectors. So there's ways to extract these elements. For example, if you want just the ith row of A, then if you multiply this matrix by a row vector, then you're going to get the ith row. So let's see. Let's come up with a 4 by 4 matrix, or it doesn't have to be a 4 by 4. Let's do a 4 by 5 matrix. Ooh, that's big. So let A equal to 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. Wait, this is a 4 by 4. I wanted a 4 by 5. Let's just add another number here. 17, 18, 19, 20. All right, so I have this matrix. If I want to extract the ith row, let's say the third row, it's easy. Just, if you know what the matrix is, you can just, I know what the third row is. It's 9, 10, 11, 12, 19, right? But the idea behind this is that if you don't know your matrix and for some reason you want to extract one of the rows, then how else are you going to do this? Well, it turns out that you could do this by multiplying this matrix A by E sub I. So that's a vector, but we have to kind of write it as a matrix. So A is, what size is A? It's what? 1, 2, 3, how many rows? 4 rows by 5 columns, right? Now, if I want a vector or a matrix that to be multiplied on the left side of A, which is a 4 by 5, Do I want a row vector or a column vector to multiply over here? A row vector? So a row vector is a 1 by how many columns do I want? 1 by 4, because I want it to match with the number of rows in the matrix. So if I want to extract the third row, I would have 1 in the third spot and 0 everywhere else. And I would have 4 elements in this vector slash matrix now. I want to write it as a row matrix. Okay? So, this is my matrix. If I do the multiplication, I would get my row times column business. Well, first of all, what is this going to end up being? What's my result going to be? What's the size of my result? It'll be a 1 by 5, right? So I'm going to have a 1 by 5 matrix. And what is that going to look like? It's going to be a row matrix with 5 elements. And if I do this multiplication, I get 0, 0, and then 9 and 0. I get 0, 0, 10 and 0. 0, 0, 11, and 0, etc. And then I've been able to come up with the third row of my A vector. Okay? You see how that happened? All the zeros wiped out all the other rows, and then all you have left is the whatever position that 1 was in. And so the same process for extracting a particular column in A. If you wanted to extract a particular column in A, you would just multiply A by a column vector. So get the fourth column of A. You would take your A vector, and this time you would multiply this by a column vector. Wait, let's get the sizes down again. A is a 4 by 5 matrix. What kind of matrix do I want to multiply this if I'm going to multiply the right? What kind of vector do I want? A 1 by 5, or 1 by 4, 5 by 1, or 4 by 1? I want a what? 5. It has to match, right? By 1. So this will have 5 rows. It would have 5 rows, and it would have 1 column. So it'll essentially be a column vector. And if I want to extract the fourth, I would multiply it by 0, 0, 0, 1, 0. Okay, so what I should come out here with is the fourth column. So 4, 8, 12, and 16. Okay? And this is a 4 by 1 matrix. And 5s go away, 4 by 1. Okay, so it's important that you know how to deal with the matrices and what to expect when you're dealing with these matrices, so that when you're looking at your answer, when you're putting a little square for your answer, you know what size of your matrix is going to be. All right. More about matrices. These things are called partitioning a matrix. It says here it's often convenient to partition your matrix into blocks with smaller submatrices that might be easier to deal with. So in this example, I have 1, 0, 0, 2, negative 1, 0, 1, 0, 1, 3, 0, 0, 1, 4, 0, 0, 0, 0, 1, 7, 0, 0, 0, 7, 2. And because of some special properties, we didn't talk about the identity property, but the identity matrix is 1. Maybe we should have talked about that earlier. Let's do it as a little side note here. You did? 1 times anything is anything? Okay. So that's really what I wanted to say about the identity matrix. It doesn't matter where you multiply it, doesn't matter what size the identity matrix is. It's a square matrix. Or if you multiply a matrix, any matrix, then you'll get the original one. And sometimes we say I sub whatever size your square identity matrix is to represent the identity matrix instead of putting 1, 1, 1 zeros in the corners and stuff. All right, so because of this special property, sometimes if you see an identity matrix embedded in a bigger matrix, like this one, you see that 1, 1, 1 in the diagonal of this 3 by 3 submatrix, you might want to be able to take advantage of that fact to be able to, in case you need to multiply something. And then you got another submatrix full of zeros. That's another another useful piece of multiplication, because 0 times anything is going to be 0. So if you partition this into a 3 by 3, a 3 by 2, a 2 by 3, and a 2 by 2, and then you proceed to do some sort of multiplication, this might make an easier product with a matrix than if you had originally taken the whole thing. Yeah, you have to do it to everything. So in this case, this matrix can be split up into 4 submatrices, and if we do a multiplication, we might come up with an easier result. And let me check your homework real quick to see if there's an example like that. Here's one. Compute this A times B by block multiplication using the indicated partitioning. So let's do this problem, one of your homework problems. You only have like 5 problems for this set. So, I don't know, something this small probably won't be worth it to partition into little submatrices. Because the work that it takes to partition and then figure out what it is you're looking for might be more work than it's worth. But I think it's good exercise anyways. Usually you want to partition matrices if it's like huge, if you're dealing with 20 by 20 or 100 by 100. or something like that with a whole bunch of zeros that you can just wipe out somehow. What we're going to do here is we're going to label each of our partitioned matrices with capital A sub stuff, and since A is since the partitioning for A gives you a two elements in one row, it looks like it gives you a submatrix or a big picture matrix, submatrix of 2 by 1. And then your B, let's call this B11. Let's call this B12, B21, and B22. So I have A1, A2 as my A matrix that I'm multiplying with B11, B12, B21, and B22. And instead of dealing with, what is this, a 2 by 4 matrix and a 4 by 3 matrix, I'm going to deal with a 2 by 1 and a 2 by 2. So what's my result going to be if I just do a matrix multiplication here? I have an A1 times B11 plus A2 B21 and then I'm going to have A1 B12 plus A2 B22 and then I have, is that it? That's it, huh? I don't need the stuff in the bottom. Okay. So we should try to figure out what these pieces are. We got A1 and B11 being multiplied together. So let's figure out what A1 and B11 is. So A1 is 2, 3, 4, 4. B11 is 0, 0. So that's a 0 matrix, right? So anything that's being multiplied by a B11 would just be 0. The only thing we should probably figure out is what is the dimension of this A1 times B11. So A1 is a 2 by 2 matrix. B11 is a 2 by 1. So what is this 0 matrix going to be? 2 by 1. So this is a 2 by 1 matrix. So this is a 2 by 1 matrix with zeros. Okay. Now A2 and B21, A2 and B21. B21 is here, and A2 is an identity matrix. So what should this product be equal to? Just the 1, 0, right? Is that right? Because A2 is an identity matrix, so identity times that is going to be, okay. So that's the second one. Actually, we can begin to write our answers, I suppose. It says 0, 0. plus 1 0. Oops, not a fraction. So that turns out to be 0, that's 1 0. Right? And now let's figure out what happens on the other side over here. I need an A1 times a B12. So the B12 is an identity matrix. So this would just be A1, which is 2, 3, 4, 4. All right, and we should always examine that an A1 is a 2 by 2, B12 is a 2 by 2, so this is a 2 by 2 matrix. Okay, and then the last bit that we need is A2 times B22. This time A2's identity matrix. So A2's identity matrix, and all we have left is B22, which is 4, 4, 3, 2. So we have that over here. We got 2, 3, 4, 4 plus 4, 4, 3, 2. And then we add those two, we get 2 plus 4 is 6, 3 and 4 is 7, 7 and 6. So that's my final matrix. And let's see, just to check make sure that our dimensions are correct. A is a 2 by 4 matrix. B is a 1, 2, 3, 4. It's a 4 by 3 matrix. And so your result should be a 2 by 3 matrix, which is the case. So I don't know if that was any easier than if we were to multiply it directly, but like I said, when you start dealing with huge matrices, this might be an advantage, especially if there's a lot of zeros and identity submatrices all over the place. Okay. The last bit of this section talks about a matrix column representation and a row matrix representation, which is kind of confusing because it looks like they're using the rows and the columns backwards, but if you look at it carefully, it actually does make sense. Maybe if we look at this carefully and realize what these things, what each of these components are. So A is an n by n matrix, B is an n by r matrix, and you partition B, you split B up into a bunch of columns. Then AB, you can look at the product of AB as A times each of these column matrices put together. So this is called a matrix, and B was split up into columns, so it's called a matrix column representation. On the other hand, if we partition A into row matrices, then AB is going to be row times matrix. So the row part is the first matrix, and the second part is the matrix. Then that's why it's called matrix. It's a row matrix representation. Now, one of the problems that you guys have in your homework is to write these representations separately and then do the actual multiplication. So I'll let you think about how this would work out in the representation. So you'll have a homework problem on this. And that would give you the illustration. And the last thing is an inner product versus an outer product. Yeah.
So in the matrix column representation that we have, what's happening between the middle commas? Are they multiplied?
Well, technically these are column vectors.
Right.
So this is one column, another column, another column.
All right, okay.
And then so if you break that up into these sub-columns, these are also column vectors, then that's your result.
All right, okay.
Again, dealing with this with a small number of rows and columns like you guys will do for your homework seems tedious, but this would be more effective if it was a larger matrix or if you want to extract certain things. All right, the last bit, I guess we're out of time, so we'll put the last bit up next time, and then you should be ready to go to do your homework for 3.1. Okay, see you guys next time.